Alright, hell yeah. So if you're joining me for this second problem, what we got here is statics. It's an engineering class. It's like I think it's a second year engineering class. You know what I mean? It's like, it's time to get real, time to buckle up. But anyway, so we're just doing all the problems. Let's go. So the radius of a length of steel cylinder, okay, so we got a cylinder, is the radius. Oh, okay, let's draw this cylinder bigger, because it's got a radius, you know what I mean? And this is where you could, I made a mistake and just thought the radius was the diameter, but no, that's the radius. Anyway, 60 millimeters, and the length is 120. Cool, so it's got some length. And so anyway, radius 60 millimeters, length 120 millimeters. Cool. If the mass density of steel, so density, use that, and it's 7850 kilograms per meter cubed. Determine the weight of the cylinder in pounds. Now this is a perfect problem, you know what I mean? Skip to the end because I'll actually do it. But we're going to do all the cool stuff in between. We have density, you know what I mean? So let's say it was just water. And you have a meter of, so this says you have a meter of steel. No one knows what the hell a meter of steel is. But if you have a meter of water, how much, what's the density of that? Well, the density of a meter of water is 1,000 kilograms in a meter of water. And this is significant because what's 1 kilogram? It's about 2.2 pounds. So what's 1,000 kilograms? Well, that's 2,200 pounds. And this is what you refer to as a metric ton. You know what I mean? So if you have 1 meter of water, this is equal to 1 metric ton. You know, what we know of as a ton is 2,000 pounds, but a metric ton is 2,200 pounds. You know what I mean? And if you want to be more accurate, it's 2,204.6 pounds. You know, blah, blah. Okay, so that's going to be kind of our first. Okay, and then what's the density of Earth? Actually, I think the density of Earth is like only like 5 to 6. You know what I mean? It's 5 point something. Because what's the density of rock? So this is density of Earth. What's the density of rock? You should know this one. It'd be cool if you took a soil science class, but it's like 2.6 to 2.7. You know, that's the density. So the density of the Earth's crust, you know what I mean, pop out a sample, it's going to be right here. But if you go deep as hell to the core, you just have pure iron. Our Earth is made out of iron, and so what's the density of iron? That's going to be 7. You know what I mean? 7 to 8, but definitely less than 8. You know what I mean? Somewhere between 7 and 8. Okay, cool. So now you know that if the density of the top of the Earth is 2.7, and the density of the middle is 7 to 8, then the average density of the Earth is like 5 to 6. Cool, that's how densities work. Anyway, and this is a good one to know. You have a whole meter of water, and what are the other densities we know? We know that 1 gram is equal to, you know what I mean, density of water is 1 gram per cubic centimeter. And let's do that one, because if we want to convert, you'll have to do this quite often. You'll have to go, you know what I mean? Let's just do it this way. 1 gram per cubic centimeter is equal to how many kilograms per meter? So convert this. So let's get it where it's real simple. So you have grams on top, cubic centimeters on the bottom. 1,000 grams is 1 kilogram, so you know what I mean, those cancel. Okay, we're already at kilograms, because what the hell do we want? Kilograms per meter cubed. Okay, now there's 2 ways to do this, and there's a bunch of ways to mess up. I'm gonna say, and I don't even know if this is a good way. Let's just say this is 1 gram per centimeter, and you want to convert it to kilograms per meter. So what would you do? Well, you'd do 1,000 grams, 1 kilogram. Booyah, did that, nothing different there. But for centimeters, you would go, I don't know, 100 centimeters is 1 meter. Cool, that's one way to do it. Centimeters cancel, and now you've got kilograms per meter. You know what I mean? You did it. Okay, so And then you can make this as complicated as you want. You can go 1 gram per centimeter, but I know that 1 centimeter is 10 millimeters. It's always good to maybe get to millimeters because it's pretty easy. I do this all the time because now 1,000 millimeters is 1 meter. Sometimes, especially with the SI units, whatever's closest to like the biggies are the meter and then the millimeter. You know what I mean? Because they're factors of 1,000. The decimeter, no one knows what the hell that is. Okay. So anyway, so the same thing here. Millimeters cancel, centimeters cancel. And then we got to do 1,000 grams per kilogram. Booyah, grams cancel. So now this is going to be equivalent. So this was 1 gram per centimeter is going to be 1 kilogram per meter. You know what I mean? Okay, and this is a nonsensical term. Grams per centimeter. What the hell does that even mean? So anyway, let's go back to this one. But it's a decent way to do it. So sometimes this could be a quick trick for you to do. So centimeters. Let's just say I know 100 centimeters is in 1 meter. Perfect. Now did we do it? Sure, but close enough. But now your centimeters is cubed. So then do this, and then cube it, and now. So what the hell does this mean? If you cube this, what you can do from math is that you can take this cube the top part, cube the bottom part. You know what I mean? So we can go 100 centimeters cubed, and then 1 meter cubed. Perfect. And we can even go farther and say, hey, we can FOIL this out, or I don't know if you call it FOILing, but we can cube 100, and then we can cube this unit. You know what I mean? So now we have 100 cubed, centimeters cubed, divided by 1 cubed, meters cubed. Now I just wish in engineering someone showed me this, because this is kind of where you get tripped up, and you just shouldn't. You know what I mean? You should find 5 different ways to get to the answer. Because now if we have 100 3 times, count up the zeros, we have 6 zeros. So that's going to be 1 million. Okay, and you're going to have 1 million centimeters cubed divided by, 1 3 times is just 1. That don't change at all. But your meters is now meters cubed. So now you have 1 million centimeters cubed is 1 meter cubed. So there's your relationship. Cool. So now we can actually convert. Let's do it. Let's go. This is, we'll do this one. We'll do 7850 kilograms per meter cubed, and we want to know what this is in grams per centimeter cubed. So I'm going to do my method and just say, hey, kilograms, I know that 1 kilogram is 1,000 grams. Okay, and I know that 1 meter, forget, just for the time being, just say the cube doesn't even matter, but I know that 1 meter is, and I need centimeters. I know 1 meter is 100 centimeters. All right, done. But now I do know that I do need to cube this whole thing. Now you can go into that. But now I would get your mind wrapped around this part. How cubing the outside means you can cube the top. But if you cube the top, that means you're cubing the 1 and cubing the units. Cubing the 100 and cubing the units. Okay, so the 1 stays the same, and the top 100 cubed, we already did it, goes to 1 million, because you got 6 zeros. So now let's just write that in. We'll cross that out and be like, hey, so we know that 1 meter cubed is 1 million centimeters cubed. So now you can just instantly cross these out. And now you just got grams per centimeter. And you have 1,000 divided by 1 million. You know what I mean? Same thing. You got 3 zeros up here, so you're going to get rid of 3 zeros. And you're going to have 1 divided by 1,000, and then multiply by this. And if you have 1,000 on the bottom's place, then that means 1, 2, 3. This decimal place goes to there, and then you're 7.85 grams per centimeter cubed. So this is steel. The density of steel, I don't even know why. I just know it's set between 7 and 8, but obviously it's already given in the problem. It's 7.85. That's the density of steel. Alright, like I said, this is the only way I know how to do these problems. So let's get a freshy sheet of paper. And we're not even done with the fluff. Alright, so let's do it. So, because the other thing to do is, like, all they want to know is how much is the weight of this in pounds. Well, because here's the other thing, is the question is how much is 1 cubic inch? How much is 1 cubic inch of steel weigh? And let's say I just gave it to you, it's 1/3 a pound. And if you want to know this more accurately, it's 1 divided by 3.5. Or that's saying for every 2 cubic inches, it's going to be 7 pounds. But it's kind of 1/3, you know what I mean? But it's more like 1 over 3. 1 divided by 3.5. Because the actual number is 0.2. You know what I mean? This gives you 0.2857. But it's 0.2. I think it's like 0.2. You know, if you did 0.29, you'd be just fine too. So some books say steel is 0.29. Other books say steel is 0.288. You know what I mean? And then a number. 9, 3, 2. I don't know. But anyway, but just in general, it's kind of good to know. So we're going to do this problem because we're going to assume you're not in Canada and you don't know what millimeters. So here's the deal. Is how many inches? This is such a good problem. How many inches are in a meter? And I'm just going to say it's 40. I'm going to give you the answer. You should say there's 40 inches in a meter, and a meter is not a yard. You know what I mean? A meter is not 3 feet. A meter is not 36 inches. A meter is 40 inches. It's closer to 40 inches. Now, a meter doesn't round to 40. It's like 39.37 or something. You know, we don't round up to 40 inches. But it's good to know that a meter is 40 inches because 100 millimeters is good enough. That's 4 inches. So I would say, hey, a meter is 4 inches. 100 millimeters, hell yeah, that's 4 inches. And then what do we know precisely is that 1 inch is 25.4 millimeters. Now this is totally exact, but you can just approximate that 1 inch is 25 millimeters. So you can be like, well, how many 25 millimeters do we have? Well, we got 4. So we got 4 inches plus 20 divided by 25. You know, this is almost 5 inches. You're 5 millimeters away from being 5 inches. You know what I mean? You're 5 millimeters away. So it sounds like 5 millimeters is pretty close to 1/4 of an inch. You know what I mean? Close enough. You know, you do you. I know it's not perfect, but these problems, especially the first chapter, I mean, this is kind of what you want to be doing, is getting yourself associated with the values, and they're usually all Canadian values. You know what I mean? No one uses inches, and thank God they don't, because else you'll just have to use slugs all the time, and no one wants that term to be uttered ever in engineering. Okay. So how would you just do this real fast is that you would be like, okay, 60 millimeters, that sounds pretty close to 2 inches. And this is close enough to 100 millimeters. I'm just going to say that's 4 inches. And instead of a circle of steel, I'm just going to square it off. So we're going to have, but this is the radius, so we're going to have 4 inches by 4 inches and by 4 inches. You know what I mean? So that's going to be... It says it's a steel cylinder, but it's look at this. The diameter of the cylinder is the same dimensions as its length. You know what I mean? It's almost a square plug of steel, and it's 4 inches. You know, it's more than 4 inches, and that way, and it's definitely more than 4 inches this way. So now we just want to know the weight of it. Well, so we know. You know what I mean? We're turning it into a square, but the values are a little bit lower. So we're just going to say 4 times 4 times 4, 4 cubed. That gives us 64 cubic inches. And you just said that 1 cubic inch was like a third a pound, or 1 divided by 3.5 pounds. You know what I mean? So so we're gonna multiply this by 1 over 3.5, and we're gonna get 18 pounds. All right, so so it looks like this thing weighs 18 pounds. And I swear, man. But let's say this was pretty close to 4.5. So you know, this 4.5 inches. Well, oh no. This is pretty close to 5 inches. Because 60 millimeters as a radius is pretty close to 4.5 inches. No, 2.5 inches. Sorry. So your diameter is gonna be 5. So we're gonna have 5, and let's just say we have 5. So we're going to go 5 cubed, 125 inches cubed, times 1 divided by 3.5. Alright, so this is going to be 35 pounds. Okay, so now I think we're in the ballpark. Now we can just do it 100%. And but this is what you want to do with first chapter problems. You kind of just want to guess to get there so when you actually do the problem that you're you know you're going to be in the ballpark. Because if somebody says, hey, I give you a 60 millimeters, see, these numbers mean absolutely nothing to me because I don't live in Canada. Yeah, so that's why I try my best to make associations. So we have something that's like 5 inches long, and then we have something that's like a diameter that's also this. So we have a plug of steel that's about this. You know what I mean? You got that much steel. If I have that much steel and I'm picking it up, yeah, about 35 pounds. It's going to take a lot of effort. So that's basically, so this is probably the best part of this video, is actually just doing this with my hands. I got 5-inch length of steel, and it's a round thing of steel. So you can imagine picking up pure steel. Hell yeah, it's 7 times heavier than water. 35 pounds. Anyway, so let's do the problem. I got to print out another sheet. Catch you on the flip side. Alright, hell yeah. Before we get a new sheet of paper, I just want to also say, you know, to me, when you do guess, you're looking at what do they call it? You know what I mean? A factor of 10. You know what I mean? How far are we off? I forget the name of this. But if we guess that it's in between 10 and 100 pounds, you know what I mean? Then that's kind of where our guess is. So our guess is that the weight of this thing is going to be between 10 and 100 pounds. For the life of me, I don't know the actual term for that. You know, like a significant. But anyway, so let's just move on and do this problem 100%. So now what we do, I think this is what I like to do. You have density, and then so I said before, the units is the equation. So the units on density is kilograms per meter cubed. So I like to do this. I like to do kilogram and then meters cubed. So literally this is the equation for density. So if someone gives me a mass in kilograms and a volume in meters, you know what I mean? Because meters cubed is a volume. That's the definition of meters cubed. Then I can figure out the density. Because this is an equation, I can also, like, what do they want to know? Determine the weight of the cylinder in pounds. Well, first I want to know the mass of the cylinder in pounds. So using density, how do I find the mass of something? Well, I take a volume, I take a meters cubed, and then I multiply by this, where the meters cubes are on the bottom, and then the kilogram is on the top. Booyah, booyah, and now I'm left with kilograms. And this was an easy one. Sometimes you got to flip it. You know what I mean? Sometimes you actually have to take this density and divide by density. You know what I mean? But in this case, if I know the volume, I can just multiply by the density, and I'm going to get kilograms. And then once I know kilograms, I'm going to use that F equals ma. Let's do this again. Acceleration of gravity on Earth, A, is 9.81 meters per second squared. And then, so this gives us an equation that if we have 1 kilogram, what's the force on that in newtons? Because F equals ma, this is an equation. Newtons is equal to kilograms meters per second squared. So now that I know if we're on Earth, we got 9.81 meters per second squared, and if I have 1 kilogram, I'm going to have 9.81 newtons. So this gives us a relationship between newtons and kilograms, so I can always say 9.81 newtons is 1 kilogram. So if I want to convert from kilograms to newtons, this is going to be your simplest conversion. First, convert your mass to a force. And then I'm blowing my mind, because what we're doing is we're converting a mass to a force. But if we do convert a mass to a force, that's dependent on what planet we're on, what the acceleration of gravity is going to be. You know what I mean? So there you go. So we're gonna say that 1 kilogram is 9.81 newtons, and then how do we convert newtons to if you wanted to find the mass in newtons, we don't even want to do that. And my conversion for kilograms is 1 kilogram is 2.2046 pounds. You know what I mean? So we're just going to do that conversion right off the bat. We're going to say 1 kilogram is 2.2046 pounds, and then booyah, we'll have the force in pounds. All right, so let's go through that process. So we need to figure out the volume of a cylinder with a radius and a length, and we know that the volume is just going to be this area multiplied by the length. And the area of a circle is pi r squared, length is length, and then so the volume is going to be just this area times length, which is pi r squared times L. Okay, cool. And if you want to do this all in one shot, I mean, this right here says that, hey, if I have a volume and I multiply by the density, I'm going to get, definitely the mass. Okay, so we're basically gonna solve that one first. And so now if I want to know the mass, I can do this. Volume times density. I know this is going to be my volume, so I go pi r squared L times the density. Now we can just do this all in one go. This is also a good application. Like, kind of once you know, I use units first to know exactly how I can get there, and then I like to, challenge myself to be like, hey, can I just get there with an equation? You know what I mean? Can I get there in one go instead of doing every little step along the way? So, all right. So we're gonna get our mass, and let's do this. I mean, holy Toledo. See, this F equals ma is so bizarre to people that we just associate kilograms. If someone says, hey, I weigh 72 kilograms, oh, cool. Sounds like you weigh, 155 pounds or whatever this is. You know what I mean? We just associate kilograms with pounds, but we don't associate that F equals ma. You must be on a planet where the acceleration of gravity is like 9.81 meters per second. You know what I mean? Giving you, so if I know kilograms, you know what I mean? So if we want to know the force over here, well, you have this F equals ma. So I'm blowing my mind right now, is that if we want to know the force, if this gives us the mass, force is just mass times acceleration. So we found the equation for mass, but we want to know force. So we have to multiply by acceleration. So this is cool. So now we got pi r squared L density times the acceleration. So this is such a cool equation that really teaches you the principles of physics where it's really easy just to be like, oh, okay, I have a radius and I have a length, so I can find the volume, and then just do that, and then be like, well, what do I know? If I know the density, I can take the volume times density and get a mass. And then if I know the mass in kilograms, I can just do a conversion factor to get pounds. But it's so much better to be like, well, no. Mass is the number of molecules in a system. You know what I mean? Especially if you're going on to like quantum physics, you really want to be thinking about stuff that, hey, matter is just a property. You know what I mean? And things that have matter and you move them to another location will probably have the same number of atoms. So the matter, probably won't change unless something like, removes it. You do have radiation maybe where you're actually losing. But anyway, it gets into that, what particles have mass and are significant compared to what particles, kind of don't have mass, even from like a radioactive decay. But yeah, this is so fascinating. I'm even blowing my mind, and I'm glad I'm taking. The whole point of these first problem things is like, hey, you're turning them into a lecture, and maybe all my problems will be this way. I just won't give you the answer until the very end. So, and I actually need another sheet of paper, but we're going to do this all in one go using this, and it's going to be so cool. And but we also want the force in pounds. But now this is going to give us the force in newtons, because we're going to say acceleration is 9.81 newtons. But then how would we convert newtons? So let's say we do get this force in newtons, and now we need to convert newtons. Well, knowing that F equals ma, and 1 kilogram is 9.8 meters per second on Earth is going to be 9.81 newtons, we can say that, hey, 1 kilogram is 9.81 newtons. I'm having so much fun this week just constantly doing this problem, because you can do the same thing in U.S. customary units and say, hey, 32.2 feet per second squared, and I'm going to have 1 slug. No one knows what the hell that is. That's why this is good to do. And that's going to equal 32.2 pounds. So now I have this relationship that 1 slug is 32.2 pounds, and I have a conversion factor here. So I'm going to get newtons, and but honestly, the only way I know to fast convert newtons to pounds is to convert newtons back into kilograms. You know what I mean? So we're going to do that, and then I'm going to do kilograms to pounds because I know that conversion factor. So I'm going to say that. So whatever newtons I get, I'm going to say that 9.81 newtons is 1 kilogram, and then I'm going to say 1 kilogram on the bottom is 2.2046 pounds. So that part will be the fluff at the end. I don't know how to actually make the equation, and it's too complicated to actually convert everything to inch. I mean, we could convert, well, you'd have to convert to feet. You'd have to convert radius to feet, length to feet, so then you'd have feet cubed, but then you'd have to find the density in pounds per feet cubed, which you could do, and then you could use this acceleration as 32.2 feet per second cubed. So maybe we should do it that way, you know what I mean, and all in one go. So yeah, that would be fascinating. And I don't even want to get another sheet of paper. I think you see what the hell we're doing. So, all right. So let's at least use our fast equation first. Is pi r squared L density acceleration, and we know the radius is and you got to convert this to meters, 0.600 meters. Our length is 0.12 meters. Because, and if you didn't know, that's 60 millimeters, and the decimal place 3 times. It's 120 millimeters, and the decimal place 3 times, and that gives you meters. Okay, and then our density is 7,850 kilograms per meter cubed. Perfect. And our acceleration is 9.81 meters per second squared. All right, hell yeah, let's go. So we're going to get pi 0.060 meters. Square it. Length 0.10 meters. Density 7850 kilograms per meter cubed. And acceleration 9.81 meters per second squared. Okay, so we're going to have cubic meters, and then the cubic meters is going to go away. We're going to have kilograms multiplied by meters per second squared, which we said was F equals ma. So this is really going to give us newtons, because that's kilograms meters per second squared. It's the definition of a newton. So perfect. So this is just going to kick us out newtons, and let's do it. Pi 0.06 squared 0.107850 9.81. Alright, so I think we're good to go there, and we get 104.5 newtons. Just quickly divide by 4, and it's approximately 26 pounds. And then, hell yeah, since we did all the work up front of guesstimating, we said this is going to be between 18 and 35 pounds. And we get 26, but this is still a guesstimate. So now we want to take this 104.5 newtons and say that 9.81 newtons is 1 kilogram, and 1 kilogram is 2.2046 pounds, and that's plenty accurate. So I'm gonna store this as x, and we're gonna go x divided by 9.81 times 2.2046, and we get 23.487 blah 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 pounds. And if we look at the units, we got 2 significant digits. You got 3 over here. You got 4 over there. You never know if this is only 3, though. You know what I mean? So any of these, and you definitely know that's 2. I mean, sometimes you might only think this is 1 significant digit. You know what I mean? Because this one isn't significant because you know they're potentially just guessing. I mean. Maybe it could. Maybe they'd know the difference between 61 millimeters and 59 millimeters. But sometimes this isn't 100% not. But anyway, that's for another video. But we could do it right here. So if I do this, 60, and I go 10 millimeters. What the hell does that even mean compared to 61 millimeters? So this says 60, but plus or minus 1 millimeter. It says this last digit is plus or minus 1. You know what I mean? And you could have something that said 625 millimeters, but the last 2 digits are plus or minus 15. You know what I mean? So it's 625 millimeters plus or minus 15 millimeters, which is really bizarre, but that's what these 2 digits mean. So that's just kind of a freebie on me. Always fun to kind of kick those pearls at you, because you'll come across this and you'll be like, I don't even know what the hell's going on. All right, so how did we do? Oh, anyway. So we wanted to know what we should round our, how many pounds is this? Well, 2 significant digits. So this thing's 23 pounds. And I don't even know if that's the answer on the back of the book. This is an even, so hell yeah. The suspense is killing you if you think I even got it right. 23.5 pounds. So they use 3 significant digits. You know what I mean? Whatever. That's the other thing. Some of these physics books will use 3 significant digits no matter what. I saw that in physics, in the physics textbook. You know what I mean? Even though they sometimes only give you 2 for one and then 3 for the other, they're always going to revert to at least giving you 3 significant figures, which is bizarre. You know what I mean? Instead of just saying, hey, there's only 2 significant figures here. And they're kicking out the answer. 23.5, that's exactly what we got, because it's 23.5 pounds. But anyway, so there you go. There you go. And a half a pound is significant. That's 8 ounces. So you would definitely know probably the difference between 23 pounds and 23.5. So I'll give you that. All right. So do you want to be done with this problem, or do you want to do it? I think we want to do it one more. I think we actually want to do it all in one go. We're going to use our equation. R squared L. And then how would you convert all this? So your A is going to be 32.2 feet per second squared. Let's just do it. So you got force, pi. You're going to have 0.06 meters. And we're going to say times 1 meter is 100 millimeters. Times 25.4 millimeters is 1 inch. Times 12 inches is 1 foot. So now we just converted this to feet. And then we're going to square it. Now we're going to take it by its length, 0.12. And I didn't really need to I didn't need to convert it to meters first. So if we have 120 millimeters, let's do it this way. 25.4 millimeters is 1 inch. 12 inches is 1 foot. That stays the same. I guess we got to go all the way down here. Our density is 7,850 kilograms per meter cubed. And now this one will do like we know what the hell we're doing. So we're going to go 1 kilogram is, well, no, we have to do our F equals ma. F equals ma, U.S. customary, acceleration 32.2 feet per second, mass is in slugs, and then force is 32.2 pounds. You know what I mean? If we have one slug and we're on Earth, that's going to be 32.2. So we know the relationship, one slug is equal to 32.2 pounds. Do this every time. And now we know that, oh, but right here, what do we want to change this to? I think we want to change kilograms per meter cubed to slugs per feet cubed. I think we want to keep with the mass per volume. So, I guess the only way I know how to convert, well, I know that kilograms is 2.2046 pounds. Now I know, so I definitely know that. I don't know kilograms to slugs, but I do know kilograms to pounds. Even these aren't equivalent. I still know this relationship. But now I know that 32.2 pounds, holy Toledo, my hair is getting crazy. All right, it is 1 slug. So there you go. So pounds cancel, kilograms cancel. And now we have to deal with the meters. So 1 meter cubed, and we got to convert that to feet. Well, 1 meter, and I'm just going to say, I'm going to do it my way. 1 meter is 1,000 millimeters. 25.4 millimeters is 1 inch, and then 12 inches is 1 foot. And now we have to cube all these. So in your calculator, the ones cubed don't change. So it's basically 12 cubed, 25.4 cubed, and then 1,000 cubed. 1,000 cubed is a billion? Yeah, holy Toledo. Okay, so all right, moving on. So now we got it. So now we can cross out the meters cubed because we converted. So the meters cubes cancel, the millimeters cubes cancel, inches cubes cancel, and we're left with feet cubed. So now we're left with slugs per feet cubed. We did it. And now we need to multiply by the acceleration of gravity, 32.2 feet per second squared. And just in general, we know that we're going to get something. We're going to get feet squared for this times feet times slugs per feet cubed. The feets go away, and then we're going to get slugs times feet per second squared. And we know from our F equals ma that 1 pound is a slug times feet per second squared. So if we have slugs, feet per second squared, this is just going to be pounds. So there you go. So that's all in one go, and it looks real crappy. Sometimes it's best to even just get rid of the units. So we're going to go pi 0.06 thousand all this squared 120 Oh, I don't even have room for this. Thought I could get it all in one go. But now you're going to have 1 over 1,000 cubed, 25.4 cubed over 1, 12 cubed over 1, and that's going to do it. Whew! Alright, let's do it. So we got pi 0.06 times 1,000, 1 divided by 25.4, 1 divided by 12. Oh, it's getting brutal. Alright, multiplied by 120, 1 divided by 25.4, 1 divided by 12, 7,850, 2.2046, 1 divided by 32.2, 1 divided by 1,000 cubed, 25.4 cubed, 12 cubed. Holy Toledo. Okay, and we get a... See, we got the wrong number. Damn it. Alright, hell yeah. I went back through there and I was just like, oh yeah, I did the whole thing. Went back through everything. I just forgot to add the acceleration at the end. 32.2. So now 32.2, and hell yeah, we get the right answer. 23.5 pounds. And booyah, that was crazy. But I like doing this. Can you do the problem all in one go? We got an equation, and hell yeah, you can do it all in one go. You just have to get your units. You know what I mean? This equation works for SI and US customary. You just got to make sure your units match. So anyway, holy Toledo. That's problem number 2, but that's the way I do things. You know, a couple things that I want to get better at is just chilling out, you know what I mean? That's why we kind of do this voice. So that's going to be 1. Maybe getting to the point. I don't mind the side tangents. I think that's actually where people are going to be more curious. That's why I don't like the whole YouTube, you know, math world and physics world, where you just do the same dumb textbooks problems and don't add anything to it. You know what I mean? Because you're not teaching at that point, you're just regurgitating. You know what I mean? But we get on crazy tangents where I just don't want to make 3-hour movies. So hell yeah, we're keeping these within half hour, you know, per problem. And each problem is kind of like a lecture. So as long as the problems are under 40 minutes and I don't get on a crazy tangent, I think we're doing good. All right, well, thanks for joining me. That was problem number 2. And this was problem number 1. But anyway, so hell yeah. So there you go. Problem number 2. So we had the length and radius of a steel cylinder, and we said, hell yeah, it was that much, and it weighed 35.5 pounds. We did it a lot. I'll come up with that term where you guess within, you know what I mean, within 10 to the 1, 10 to the 2, 10 to the negative 1, 10 to the 0. You know, each of these. There's a physics term that says, hey, can you guess within a factor of 10? You know what I mean? That's significant. Like how many pounds do you weigh? Do you weigh 10 pounds? Do you weigh 100 pounds? Do you weigh 1,000 pounds? You know what I mean? Is there one of these that you could guess you weigh 0 pounds, 10,000 pounds? Is there one of these you could guess that's the closest? Probably. You know, sometimes there's one where you can guess, like I know I weigh in between these two. You know what I mean? You know, I guess it's not quite obvious if someone weighs pretty close to 100 pounds, whether they're close, whether they weigh in between 10 and 100 or 100 and 1,000. So there's a couple different guessing strategies, but I'm definitely going to employ a lot more guessing strategies per these videos because I find that so fascinating with physics. All right, we got to end this one. Thanks for joining me, and that's a video.